Hello everyone, welcome back to 3 Deviations. So in the last video, we covered the introduction to work. We introduced the concept of work as this physical quantity that is used in all types of classical mechanics in the field of physics. So this is one of our first applications to the sciences that we have in integral calculus that we have dealt with so far. So we've introduced work as a quantity that is equal to the product of force and distance. And we've also used the second Newton's law, which says that force is equal to mass times acceleration, with acceleration being equal to g being equal to 9.8 meters per second squared. So we've also generalized work to be more useful in instances when we have non-constant force. So we say that that's equal to the integral between start points and end points, which I will call A and B, as we have for a very long time, and that is of our force times our little displacement, ds, I like to call it. You could call it dx. It really depends on what you're working on. Your variables are probably going to change. So this work problem is going to be a little bit more challenging. It's probably something that you will have seen in an AP Physics course or perhaps a Calculus 2 course. We're taking this example from James Stewart's calculus book. This is problem number 17 from section 6.4. Okay, so this problem says that a leaky 10 kilogram bucket is lifted from the ground to a height of 12 meters at constant speed with an 0.8 kilogram per meter rope. Now the bucket contains 36 kilograms at the beginning, but the water leaks out constantly and finishes draining as the bucket reaches 12 meters. Now determine the work. I'm going to write our work equals force times distance and our F equals MA equations, just so that we have those ready for easy use when we need them. Okay, so first we should determine our known quantities. We know the mass of the bucket is 10 kilograms, and we also know that the length of the rope is 12 meters. Our height is 12 meters. We're lifting the rope 12 meters. So any integration that's going to happen is going to be happening between 0 and 12. Okay, so we also need to determine the mass of our rope. So we have the mass of a section of our rope. So we have the mass of a meter long of rope, and that is 0.8 kilograms per meter. Now we also know that our rope is going to get lighter as we lift it up, so we multiply that by the amount of meters that we have left times the amount of kilograms per meter. So that's 0.8 kilograms per meter times 12 minus x meters. That gives us 9.6 minus 0.8x kilograms. So now we're starting to see our x variable that we love so much. It's coming back. Alright, so now we also need to determine the mass of the water. So we're going to do this in a fairly similar way. Now, the mass of the water is going to be 3 kilograms per meter. So we can now do the same kind of analytic work that we did with the mass of the rope. So the mass of the water, it's draining constantly. So we're going to have 3 times 12 minus x, and that's going to be 36 minus 3x kilograms. So now what we can do is we can determine the total mass of our system. So the total mass is the sum of the two masses, the mass of the rope and the mass of the water. So we are going to have 9.6 minus 0.8x plus, we open a parenthesis, 36 minus 3x close parenthesis plus 10. And that is equal to 55.6 minus 3.8x kilograms. All right, so we also need to add, of course, the weight of the bucket. Sorry, I should have mentioned that. We're adding the weight of the bucket here. Okay, so now we can plug this into F equals ma. We know the mass, and we know that gravity is equal to 9.8 meters per second squared. So we have F equals ma, and now we have our force being equal to 55.6 minus 3.8x kilograms times 9.8 meters per second squared. Now we can determine our work, because now we have our force. We also have our distance. We're pulling it to a height of 12 meters, so we know that our distance is 12. So now we can plug this in. The work is equal to the integral between a and b of f ds, which is equal to 9.8 times the integral between 0 to 12 of 55.6 minus 3.8x dx, which is equal to 9.8 times 55.6x minus 1.9x squared, evaluated between 0 and 12. And now once we do all of that math out, that's going to approximate. So we should always be careful that we're using an approximation symbol here. 3857 joules, so 3,857 joules, and that is the solution for this work problem. The next video we are going to be talking a little bit more about work, and then we're also going to be introducing the average value of a function. That's our last topic in Unit 5. Thank you very much for watching, and we'll see everybody in the next one.